In just a second. Let me get started.
See y'all. Have a good class.
All right, I will attempt to begin with a word of prayer here. So, dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask that you'd help us use this time wisely to help review for the final and just complete the semester. Lord, in your name I pray, Lord Jesus. Amen. All right, so let me get my computer up and running here. So, firstly, I should mention, final exam-wise, time-wise, like I think there are 5 times that I'm giving finals, technically. And if for some reason you don't feel like taking our final when it's scheduled and you want to take it at one of my other final exam times, I don't mind if you do that. But these are the times that I offer finals. So like, you know, I don't know if that is something you're interested in or not. If it is, just email me. So, also, I'm about 95% sure this is right, but I also don't trust myself because I'm kind of sick. So I'm going to go home and double check these times and dates and make an informal announcement about it. But just I wanted to tell you now to look for that announcement later, all right? Let me see if I can find my solution. All right, so let's talk about test 3. And I will get you your test so you can look along. What is this exactly? Like Nature's Nectar. Like what brand is this? Is this? Do you guys know? I mean, ideally, it's got a flavored juice drink blend from concentrate with other natural flavors. It's very sketchy though. Well, it's good till September 9th, 2025. I guess I'm okay. And maybe I should have gone with a soda of, there was a soda in the math department of kind of ambiguous origin. So this was what I was trying to do on your quiz, and I failed miserably, as you remember. As you experienced, I suppose I should say. So with them, so first of all, -1 to 1, and I made it even and odd, so the product of even and odd is an odd. And that integrates to 0, so they're already orthogonal, so all you got to do is normalize them. So we calculate the length squared and the length squared, and then we have to divide by the length. Some of you multiply by the length. Sorry. We got to divide by the length. So to divide by the length is to multiply by the reciprocal of the square root of the length squared, of course. So that. Of course, this could be simplified to the square root of 105 over 4, but I don't care. So, I guess I care tiny amount, but not enough to write it. You know, I think everybody got problem 2 right. I said it might be on there, and I didn't change it. But you didn't know I wasn't going to change it. You might have tried to like done some sort of like super double fake and not study the stuff I said that might be on the test. Because I was like trying to trick you. But you didn't think that. I'm not that tricky, is your point. I'll do better next semester. But that was good. Although a lot of you guys got that on the quiz too, so. This one here was homework. So in the homework, to prove the rotation matrix, the form of the rotation matrix in 3 dimensions, in the process of doing that calculation, you would have stumbled upon this little theorem. Well, if you'd read the solution, I suppose. But anyway, so the thing is, the rotation matrix has R transpose R equal to I. It also has determinant R equals to 1, but you don't really need that here. So x dot x for the eigenvector is, I can insert the identity here, then use properties of the dot product or the inner product, if you like, to move the transpose, which is the adjoint in this context, over to here. It unadjoints it back to R. But then this is lambda x, so you get lambda squared x dot x. So that forces lambda squared to be 1 because x dot x is the length of x squared, which is not equal to 0. So yeah, that you guys had trouble with that one.
That requires actually remembering properties of rotation matrices.
Yes, you should know the definition of a rotation matrix. That's true. I do expect you to know that. That is true. Let's see here. So what we got here? Suppose V is, I guess I don't have too much to say. I think everybody got this one, or a lot of people got this one at least. So I don't, if this is homework or if this is part of a proof in class, but on the screen. Well, yes, but the reason I have this here is because it's something I proved in class, or it's something I got directly from a homework. I think section 6.3. Those handwritten PDFs, you know? Yeah. This one here, I'm slightly dissatisfied with this in the sense that, like, I feel like I should have reminded you that the T adjoint acting on x2 is the conjugate of lambda times x2. So I'm a little bit dissatisfied with that just needing to be known in the middle of this proof, but, you know, there's that one. And so the main thing you need to know, of course, is that when we move T to the other slot, as we proved, you get the adjoint, right? And also, this gives us lambda bar, but when we pull the conjugate out from the second spot, we get conjugate, also known as the thing again. But then they're distinct, so that means that they're not 0, which means that the inner product of x1 and x2 must be 0, so they're perpendicular. So there's that one. This one here, if we have a self-adjoint linear transformation, prove the eigenvalues are real. This is not the only argument. Like, some of you guys gave a slightly different argument, which was also good. I forget what it was, but here's how I did it. You know, this, bring the lambda inside, change it to a T, move it to the other spot, make it a T adjoint, but it's self-adjoint, so that's T again, which gives you lambda, but then when you pull the lambda out, you get a lambda bar, so then you got this equal to that, which forces lambda to be equal to lambda bar, which is to say that it's real. So, yeah. So a complex number being equal to its conjugate defines real for a complex number, by the way. Problem 6. This was, in some sense, new. In some sense, not, I suppose. So here, I didn't say that G was a metric, right? I didn't say that. It's true, right? It's true that if we write that formula, x transpose gy, that makes it a bilinear form on Rn. And it's symmetric because G transpose is equal to G. That's true. But I didn't say it was a metric. I didn't say it was bilinear form. So you really shouldn't just assume the bilinearity here. You should give me evidence for it. Most of you did. It's like maybe one person just assumed that G of Cx plus y was C G of x comma s plus G of y comma s. But I can see why you did that. So I don't think I took too much off for that. But we can show that from what's given, right? And so it's just this. So I mean, technically speaking, maybe I should have had like A, B, C. And like part A is show G is a metric. you know, and then part B is this, and part C is what A is now B. But anyway, so we have this, but we're given that these are 0 if x and y are in the perp, which shows you that an arbitrary linear combination of vectors in the perp are in the perp again. And then a couple of you lost a point because you have neglected to show me that the set is non-empty, which is an important step in the subspace test, right? Wait a minute, did I not take a point off and I should have? Is that what I'm hearing? I feel like I'm hearing that. What's that? I should just subtract 5 from the score to make fair. Okay, you can do that. No, don't let me know if I made mistakes grading if it helps you. I don't want to know. Okay, so I have enough points. I don't want more. So for part B, so these are called G-orthogonal transformations. And a G-orthogonal transformation preserves the, you know, the G metric here in their product. And that gives me this equation, A transpose GA equals to G again. And then if I take the determinant of that equation, the determinants of G cancel out, and we're left with the determinant of A squared, which makes it plus or minus 1. So some of you got the matrix equation, but you didn't take the determinant of it. Like, that was like, I was like, oh man, so close. But, oh well. So I'm very pleased with what I saw in this question overall. I think you guys did really well in this because this wasn't exactly, I don't think this was exactly in the homework. It wasn't on a quiz, I don't think, was it? This was kind of new for you, wasn't it? The question, the way it's been asked, like I don't think we did this before, but you guys did pretty well on it. I was pleased. This question, whose question is this? What? This is not Daniel's question, no. This is your question. Yes, this is your question. This is Sam's question. Because Sam said something in passing about, isn't the annihilator like the perp? And I was like, yeah. Yeah, it is. So let's explore that. So that's what this is about. And there's got to be a bunch of different ways to solve this. So I was on the cusp of dropping this question from the test, but one of you almost solved it, even that person does have, at least from the look of what I saw when I graded it, that they have thought of the abstract vector as a column vector in a spot, but the larger idea was very similar to what I'm showing here, so I didn't take off much because it was close. It was close, and because of that person, I didn't drop this question. That person, whoever they are.
Doe? Lynching or something?
I didn't say it was that person. So anyway, let me run through a potential way to solve this. And we're going to learn some things along the way here which are interesting. So any kind of problem like this, almost certainly the first thing you should do is define a basis for the subspace and extend it to a basis for the whole space so that you have that to work with. That anchors your calculations in a way which is constructive and useful. So that's what I do. I take a basis for the subspace, I extend it to a basis for the whole space. Going back to that, you know, basis extension day we did, remember we proved these things in general. Stupid generality that I've never returned to ever again in this course, right? That one day we did stuff in infinite dimensions that was like very highbrow. We have not been at that level since that day. Anyway, so at this point I'm like, I have a previous argument, a previous attempt at this where I did it without orthonormalizing the basis. And I got so far, but at some point it gets really, really technical. And I decided I should try to redo it and just make an orthonormalization of the basis early on, because I had a suspicion it would make the argument easier, and it did. Because we can do that, right? We have the Gram-Schmidt algorithm. We're in the context of a finite dimensional real inner product space so that we can orthonormalize, right? And so I do that, and you know the process of the Gram-Schmidt, it preserves spans, right? So I know that as I Gram-Schmidt my original basis beta, the first k things are still going to serve as a basis for W, but now orthonormally so. And no, check this out, right? With respect to an orthonormal basis, the components of the metric are what? They're that. Right? So, of course, we can also talk about the dual basis, as usual. So there's a couple things to grapple with here. And the things I'm talking about in this problem, I mean, they're relevant to this problem. Let me flip over to the next page for a second. They help with this problem, but they're also like, there's about a half a dozen different questions which all are kind of centered around this same can of worms, you know? So don't ignore this problem just because it's complicated, because it holds the keys to other problems as well that are simpler. Anyway, so the annihilator of W, I'm going to claim it's the span of the part of the dual basis which is dual to the basis, part of the basis that's not the basis for W. The complement of the W basis, really. So first of all, notice that the annihilator is a subspace of the dual. So that means I can find whatever's in the annihilator, I can write it as a span of the dual basis, right? In particular, I have alpha is a sum I equals 1 to n of alpha I upper ui. All right? So I have that. But then, since it's in the annihilator of W, if I feed it J, where J is from the W, you know, from the basis for W, Uj is an element of W, which means that this is 0, right? But this is also what? Well, this is also, of course, alpha J, right? We've done this calculation like 20 times. So if I take a dual vector, I let it act on the basis, it picks out the component with respect to that dual basis element. So that's alpha J. That has to be 0 for 1 to n. What does that mean? Well, that means that alpha is the sum of the rest of them, which means that these are a generating set for the annihilator, right? Is it a basis for the annihilator? It spans it. Why is it a basis? Well, that is a subset of the dual basis. The dual basis is linearly independent. A subset of a linearly independent set is linearly independent, right? This is a basic truth that you should be able to prove. Proving a subset of a linearly independent set is linearly independent is a question you'd love to see on the final, right? I mean, that is very, very easy. I almost can't put it on the final because it's too easy. It would be really difficult for me to grade it, honestly. No? I see some no's. Interesting.
Why would it be hard for you to grade it?
It's just so obviously true. When I ask obviously true things, you guys find a way of like, well, half of you would like do a proof by contradiction is what's going to happen. So, but anyway. So, joking aside, that is the basis for the annihilator, all right? So this is a linearly independent spanning set for the annihilator, and hence it's a basis. Let's go back to the others. So you're trying to show two sets are equal. There are kind of like two ways to go, right? The one is just to straight try to show the double containment, right? Pick an arbitrary element in set A, show it's a subset of set B. Take an arbitrary element in set B, show it's a subset of set A. You get A equals to B, right? But since we're in linear algebra, it may be more productive for us to try to show that the basis, to try to find the, to study basis, basically, instead of an arbitrary element, study the basis. So that's what I do here. Two, and I'm not saying that this proof is like the most excellent one, it's just the proof I found at the moment. And I'm kind of sick, so, take it for what it's worth. Why, in the perp, bad people, then y is perpendicular to the basis in W, right? which means then that y is equal to this. This is a general truth. Why can I write this? Why can I write that? Do you understand why I'm writing that? Yeah, because we're using an orthonormal basis. So with respect to an orthonormal basis, the components of the vector with respect to the basis are obtained simply by the inner product. So this is because we have made ui an orthonormal basis. I can do this. I can't always do this, right? If the basis is not orthonormal, you know, you might have to divide by something. Who knows? It could be uglier. Generally, finding components with respect to a basis for an arbitrary vector requires like calculation of an inverse matrix, right? We've seen that earlier in the course. But orthonormal basis, super nice. Here's the components. But we also know that the first k of these components are 0. So we're just left with k plus 1 to n, which then says that y is in the span of the part of the basis that complements the w basis. Hence, this is a basis for w perp, right? Well, this is hopeful because at least the sets I'm trying to show are equal. They have the same dimension, right? They're both the same size. So, but if I was just asked to show that, if I was simply asked to show that the annihilator of w and the perp of w were isomorphic, I'd be done. I found a basis for one, I found a basis for the other, I've showed that they have the same dimension. Therefore, they're isomorphic, right? Two vector spaces of the same dimension are isomorphic. What's the isomorphism? Simply take the basis to one and map it to the other and extend linearly. That defines the isomorphism. But we're not asked that here. We're asked to show that they're equal. We're asked to show that the musical morphism of the annihilator is the perp, or the musical morphism of the perp is the annihilator, if you like. So, going on. I found some things that I think are kind of interesting. If I calculate the metric components here, I get the identity, right? The Kronecker delta ij. That means that the inverse metric is the same as the metric. It's also Kronecker delta ij. So the musical morphisms simplify a bit with respect to this orthonormal basis. In fact, this is that. So in short, if I take the sharp of the jth dual basis, I get the jth basis. And then likewise, if I take the flat of the jth basis, I get the jth dual basis. It's sort of like the dumbest thing you could think of possible, right? Now, so notice that then the sharp of the basis for the annihilator, right? The image of this set under sharp is that. But the span of this is the annihilator, and the span of that is the perp. And since sharp is linear, this proves that the sets are equal. This is not the only way to prove this, all right? And the other proof I have, I was just going with double containment, and I got pretty easily to one of the double containments. But when I tried to go the other way, all of a sudden it was like, brain hurting, have to think, you know. But anyway, so enough about that. This was supposed to be a gift, but it was not taken as such. There was much suffering here. Much suffering. So much suffering. So in the homework, I had you guys do something similar to this, but instead of instead of BV, I had BV dual, right? And so for BV dual, you build it with the tensor product of V lower I, V lower J tensored, you know? But anyway, just to get to the point, you take a bilinear form, let it act on a pair of vectors with respect to the basis, pull your components out, you've got some numbers here, the coefficients of B, if you will, this right here can be rewritten as, so one of the things I've tried to say a little bit in this course, but maybe I haven't emphasized quite enough yet. If you lack a mental image for what the dual basis is, think of them as the component functions to the coordinate map. That's what they are. So like this is the ith component of x with respect to the basis beta. Or it's the ith component of x with respect to the basis beta. This is the ith coordinate function. It's picking off the ith coordinate. Likewise for that. So, of course, this, the fact that this is equal to this, we've worked out before. This is like test 2 stuff, all right? But anyway, so this is that. And then in terms of the tensor product, that is vi tensor vj acting on x comma y. And then I'm taking a sum of such maps. So I just look at it in the totality as a sum of maps acting on x, y. But this holds for arbitrary x, y. Consequently, B is the sum of the tensor, sum of the the weighted linear combination of these tensor products. And of course, that's in the span of gamma, where gamma was defined to be the set of all these guys. And then linear independence follows from a short calculation. If you suppose you've got a linear combination equal to 0, feed it the basis, KL, get your Kronecker deltas, out pops CKL being 0, therefore gamma is linearly independent, and hence it's a basis for B dual. The bilinear forms over V. So, I think everybody should be able to get a question like this if I was to ask it on the final. I think that there's hope for this question. Short of self-fulfilling prophecies, but yes. So, okay, so this one was also a play on the homework problem that we had, where I used the eigenvectors to build the matrix, remember? And so for me, so a lot of you guys have assumed that V1, V2, and V3 were the standard basis. I didn't say that. They're just orthonormal. And as such, that doesn't mean that they're E1, E2, E3. It does mean that if you look at left multiplication by A with respect to the beta basis, where beta is, this, then the matrix is diagonal with diagonals 36, 16, and minus 5. That's true, and one of you did that. But several others of you just told me A was equal to the diagonal matrix with these numbers, which is just not the case. That is not known. But at least one of you saw through my schemes and just said, oh, so eigenvalue 36, 16, and minus 5. So coincidentally, they sum to 47. What do you know? But and then this part B, you may or may not remember we proved Sylvester's theorem, Sylvester's law of inertia. An important step in that was to modify the basis by dividing by the square root of the absolute value of the eigenvalues in order to achieve 1s and minus 1s on the diagonal. So this is just that. So to make that happen, I just do, square root of 36, square root of 16, and I would have had all perfect squares, but I just don't know how to add perfect squares together to get a 47 yet. Any help on that? 42. No, I'm past 42 now. I've moved on to 47, yes. 47 once? Thank you for that. So anyway, and down here I actually prove that the ijth component of this is in fact what you want. So when you have a number divided by its absolute value, it's either 1 or minus 1, depending on whether the number is positive or negative. All right, and then moving on here. So we spent, I don't know, 30 minutes proving the Cauchy-Schwarz inequality. If a professor spends that amount of time on a proof like that, you maybe should... Anyway, your choice was right. The other one's easier. Good choice. The Cauchy-Schwarz is not easy. It's good I didn't force that on you, right? Because none of you picked it. And I wouldn't have, if I was you, I wouldn't have picked it either, right? And in fairness to you, if I was more organized, I would have warned you that was a possible test question. So part of the reason I didn't force it on you was I didn't know for sure you'd studied it. If somebody had studied it, I wanted to give you a way to reflect that, you know. But it is not an easy thing to prove. Okay, there's like a trick there and stuff. But anyway, you want it to be on the final? That's what I'm hearing.
Just bonus.
A bonus on the final. I'm not sure I want to grade it, but maybe there's something in the proof I can test. I don't know. I'll have to look. Okay, so problem. She does not learn. so this this is a dangerous question to ask because you guys are very tempted to remember one of the many litany of theorems we have, which are essentially logically equivalent to this. But you know, if I ask a question that's worth 30 points, I'm looking for some kind of substantive argument to show that that structure stems from other structures, right? So if it's like one line and it's almost the proof already, you're probably not doing it the intended way. But so here's my argument. I take W is got this basis, W then extend it to a basis for V, Graham-Schmidt the thing to get an orthonormal basis, normalize it to, why not, for kicks, and you still got a basis for W. Some of these arguments probably look familiar because they're kind of the same arguments I used in the other problem. If Y is in W perp, then I can build it as a span of the basis, but since it's in W perp, that forces part of the span to die. You know, like 1 through K, they're gone, and we're just left with the last part that's got to be in there. So thus, this is I think we proved this already on this solution. Why didn't I just say, look at the previous problem? I'm a dummy. Anyway, so we did this already. So yes, W perp is got a basis which is formed by these guys. Therefore, we can count the dimensions. We've got K for W, N minus K for the perp. And we happen to know this theorem here, right? The dimension of W plus W perp is dimension W plus dimension perp plus the dimension of the intersection. This is N, K minus K, N minus K plus this dimension. But this works out to N. This is a subspace of an N-dimensional space, right? And one of the fundamental things we know is that the dimension of a subspace cannot exceed the dimension of the space, right? So since this is less than or equal to N, that forces this to be 0. Consequently, we find that the dimension of, we also find, similarly, part of the same thought process. Not this doesn't imply that. I'm saying this and that follow both from the above equation and inequality. Namely that W plus W perp has to be N, which is to say that they sum to N and their intersection is 0, which is to say that the direct sum is W perp. Now, you don't have to use, I don't think you have to use the, if you look at this, we don't really need to use this is kind of like, you know, killing a mosquito with a sledgehammer or something. Like, we don't need this beast of a theorem to do this, right? Like, you can do everything I did up to this point, and we can be like, prove that the intersection of W and W perp is 0. That's pretty easy, right? What? No? It's not easy? Yeah, I think it's easy. I don't think it's that hard. So I'm pretty sure we could prove this by a standalone argument. And once you know that, you just need to know that the W plus W perp is equal to N. But you see that, like, the dimension of, well, I guess you kind of do need this. I don't know. Someone was trying to pressure me into testing that on the final. I don't know if I'm, not this per se, but like the more general theorem, you know. You know what I'm talking about, guys? There's one. This thing. Let me use S and T. I don't know, V and W, V and W. I didn't prove this in class, and I find this to be a somewhat challenging proof. It's a good proof to like practice on, just to see if you're really understanding basis extension type arguments and such, linear independence in the abstract. This is
That's a different formula than the one you used up there. You have a minus where you have a plus, and you have a 1.
That's definitely supposed to be a minus. Yeah.
Oh, yeah.
Oh, wait a minute. If that's a minus, oh, my argument falls apart. Oops. Scratch this out. So apparently, yeah, apparently I actually do need to show that W intersect W perp is 0. My bad.
Well, I'll give you an argument for that in exchange for some points.
I think I already gave you points, though. So, well, but I needed them intersection to be 0 to get the direct sum is the thing. I'm trying to prove that. I can't use it, you know. I'm very, very happy with this take-home test question. Like, this was like just shockingly not, it was like not stupid in the sense of being utterly trivial, but it also had no ugly numbers in it. I just made this thing up and it turned out so pretty. Like the inverse matrix is integer. That never happens, you know? So like, there's the metric components, 1, 1/2, 1/3. Those are nice numbers. And it's a 2x2 matrix, which is fun to invert, right? And the inverse ends up being this. I think everybody got this. I think everybody got it. Most people got B. You guys are a little shaky on part B. Even people who got it right. Components are numbers. I asked find the components of alpha. So these are the components of alpha. Some of you, like 3 of you, have just written alpha equals to 1 v1 plus 2/3 v2, upper 1 and upper 2. And that's not wrong, but to be fussy, that's not the components. That's the expansion of alpha in the dual basis. I'm making a very stupid distinction here. I'm just saying that if I ask to find the components, you really should find the components. I'm kind of embarrassed to even be saying what I'm saying right now, honestly. Except that I feel like there is a slight, I wouldn't even say it if I didn't think that there was a little bit of daylight between those two concepts and what I saw written. That's all I'm saying. So, to calculate the components of a dual vector, all you got to do is act on the corresponding basis element. So the component of the V upper 1 is alpha acting on V1. The component of the coefficient, if you will, the component with respect to V2 of the dual vector is alpha of V2, which is x here. So I just have to calculate those. And by definition, that was integrating x times 2x times 1 and then 2x times x, I think, which gave me this and that. But and then the musical morphism actually kind of worked out neat in the sense that this term ends up canceling, and it just leaves you with this one and twice that. So 2x was the, and then as a check, and actually after I wrote this down, I was like, oh, that's interesting. Check this out. So like if you look at this, so we know that the musical morphism, the sharp of the dual vector, it's supposed to be the Rietz vector, right? So we can check here, does it work? Well, I want alpha of f of x to be g of f of x times Rietz vector, right? But what is the formula for alpha f of x? It was integrate f of x times 2x dx. This is literally the definition for that. If I had been thinking more, I could have avoided a lot of the calculation and simply written down from the theory of the Rietz vector that the sharp of alpha is 2x. Technically, I could have avoided this calculation and just written down part C. If we remember the theorem that the Rietz vector is the sharp of the dual vector, right? So anyway, yeah, so that's test 3. Do you want guys to go back and look at test 1 again?
For part B,
Test 2? What?
how does that compare to taking the inner product of the basis?
Well, the other thing you could do in principle, I suppose, would be to multiply the G inverse matrix by the components of. Wait, which one were we talking about?
Part B.
Part B. What are you asking? I don't.
Could you also do that by finding the basis and then taking the inner product of that? Because there's an inner product space. So like finding the upper one and the upper two.
Well, but
Do
V.
we have an inner product even defined on this space?
I mean, the inner product was defined to be. Are you? I'm not sure I know what you're asking, Sam. Are you asking about like the dual inner product or?
Yes. This is just the inverse of the normal one.
That's like we can't do that here because we don't have an orthonormal. We don't have an orthonormal basis, as is evidenced in part by the fact that this is not diagonal, right? If it was an orthonormal basis, then if we're working with an orthonormal basis, this should have been the identity, and this would have also been the identity. But we're not, so yeah. I heard a request for test 2, is that right? Is correct? Yes, no? Do. I thought I had a solution here. Just a second, I have trouble seeing things. There it is. So what about this one? You just want to like look at it, enjoy the ambiance. I mean, that's the idea. All right. We can chill. Hey. Oh, I like problem 2. Forgot about that one. Let's see here. Something we haven't talked about recently, but is really important to the course, is the notion of isomorphism, right? So like constructing isomorphisms, proving this and that about isomorphisms. That's something that you should think about, all right? Definitely. Of course, I don't know, what I need a question. I don't want to just work through the whole test again. So this was what? This was the rank nullity theorem, right? So I think a lot of you guys got that. Some of you got that.
That's just the same as the W that they from the last test.
It is WW, like you think the rank nullity is like the WW perp?
It's the same problem.
It is very similar. And if you study this, you'll find out that the proof of this is also very similar in nature. It also involves starting with a basis for like, oh man, I'm trying to remember. I mean, like I said, the proof of this is interesting. It's in my notes. I just didn't do it in class. Let's see here. So general point of order, like be careful not to give me column vector arguments when the problem's an abstract vector space. Like this does not generate significant amounts of partial credit. It does the opposite. That's a serious error here. Like, you need to think about where you are and what you're doing in terms of the problems. Like, if it's an abstract vector space argument, you can't just do something with column vectors unless you choose a basis and then convert to column vectors and do things. But you do need to actually write down, I'm picking a basis, I'm looking at the coordinate vectors of this vector or set of vectors, I'm doing blah, blah, blah. Like, those steps are critical because they indicate the difference between a 221 student and a 321 student, right? Anyway, this one here, I think we just keep talking about this. Like, I think I've gone over this stuff like a bunch of times now. It's that thing again, isn't it? I do love the symmetric and antisymmetric matrices. They do make a very nice example. You know, finding the basis for the symmetric matrices, finding the basis for the antisymmetric matrices, n by n, is interesting and important. We have done it, and some of you didn't get it the first time we did it. If I come back to it, I hope that you do better. It's been a minute since we've studied quotient vector spaces, but those were actually not that bad in the big scheme of things. Like, basically, and I think this is a nice problem too, like, prove the dimension of the quotient space is the dimension of V minus the dimension of W. And like almost every other thing that you'll get stuck on in here if you're having trouble, it starts with picking a basis for W and then extending it to a basis for V, and then arguments happen, right? Depending on the definition of the coset and everything. But like that, pick a basis for the subspace is like it's oftentimes the thing that keeps us from making progress, not doing that step. Not everything on the final is going to be theoretical abstract linear algebra. There's going to be computations, right? I'm going to ask some questions about, like, you know, there should be subspace test theorems, right? There should be find a basis for this, you know, kind of set. There should be some sort of like 221 style questions about, like, finding the basis for a null space, stuff like that, you know. Not probably that exactly, but things that boil down to that, but being asked in, like, the context of polynomials, something like that. As you guys know, I love the wedge product. The thing to know most about the wedge product is that it defined for us the determinant, and also we have an extension to how the how a matrix multiplies a wedge in this, you know, definition here. I would probably try to test on eigenvectors, generalized eigenvectors, Jordan form, real Jordan form, minimal polynomial, characteristic polynomial. Like, these things are important, and many of you understand them, and I think those will make for relatively easy questions, because it basically, once you understand the machine, it just becomes a point of trivia, right? Like, you're just trying to understand, like, this matrix has that pattern, so it's therefore this thing, you know. The other thing to notice, what are the big theorems about eigenvalues? Like, let's think about this for a second. The big theorems about eigenvalues, there's really, what, maybe a half dozen of them. The trace is the sum of the eigenvalues. When is that true? Yeah.
Existence and basis.
Then what?
A diagonal matrix, existence and basis.
Oh, but it's true more than that. It's more generally true, yeah.
You can diagonalize a matrix by multiplying by a matrix and it's
But we can't always diagonalize a matrix. So the trace formula is more general than that. Like, the matrix as a trace of its eigenvalues is true for any real matrix, with the proviso that we allow for complex eigenvalues. It's just true for any complex matrix. The reason for that is that that formula is manifestly true for the Jordan form. The Jordan form has the eigenvalues down the diagonal, and any matrix is similar to the Jordan form. So because the trace is because the trace of the Jordan form is the sum of the eigenvalues, and because the trace of the matrix is equal to the trace of a similar matrix. Have I told you guys my idea? I guess I haven't told you guys my idea. I have this idea. What's that? Class is over? What? When did it end?
3 minutes ago.
3 minutes ago? Oh man. Come on, I don't want this class to be over though. I like this class.
What's your idea?
Let me finish this stuff about eigenvalues. So the trace is the sum of the eigenvalues. If the matrix doesn't have eigenvalues, it's hard to write down that formula, right? So, but the thing is, if we allow ourselves to complexify the real matrix, there's always the complexification of the matrix has a complete set of eigenvalues because the complex numbers are algebraically complete. The other thing is the determinant is the product of the eigenvalues. That's nice to know, right? Another important thing to know in this realm, the Cayley-Hamilton theorem, right? If you plug the matrix into the characteristic polynomial, it's 0. Also, the minimal polynomial has the same factors as the characteristic polynomial. And what I think, Sam, you told me this one day. When is the matrix diagonalizable? Is if the minimal polynomial what? Just has what kind of factors? Just all the factors have power 1, right? It's just linear powers. So beyond that, like we proved linear independence of the chain of generalized eigenvectors. Remember that? On this last test we had perpendicularity of distinct eigenvalues for a self-adjoint operator. You probably thought I was going to ask on this test that orthogonal implies linearly independent, right? Non-zero. That might have happened. It almost happened. I deleted the question. Sorry, Daniel. Oh, so the idea, fine. We'll end with the idea. It's a good enough place to end. So I have this idea, because we have a problem with students being hooligans in the hallway. And I was thinking, if all the students had to wear a collar, we just have like a collar everybody wears, and then we could set up like some monitoring stuff in the hallway, artificial intelligence, lots of imaging, And what it would do is it would just watch for students. If students were like outside of a room when class was going on, or maybe class is just a little bit overtime because professor really loves the class and wants to impart wisdom before it's too late, something like that. Anyway, so the students are outside and they're talking out of place. So the system, it would just give them a gentle but noticeable shock. So, it's just like that. And also, like, if people are like congregating at the nexus of two hallways, like where they're not supposed to be, and just talking, ignoring the fact that people are trying to walk there. If there's two there doing there, the shock will be small. 3, the shock gets a little bit more. But by the time there's 4 people talking at the intersection 2 hallways, the shock is unbearable. They have to disseminate. They have to separate. They have to leave.
See, I don't think you have to boundary something like that because people can talk about their being shocked, but they can't talk about their being choked. So if they're wearing a collar anyway, it tightens up whenever they're talking in the wrong spot.
You replace the shocking with choking.
Yeah. And like the tightness of the choking.
That's beautiful. The student has become the master. This is wonderful. I also have some ideas about lasers enforcing dress codes, but I won't say those. I won't say those for YouTube. But yeah. But we would do all of this with artificial intelligence, and so my great regret is that I didn't write this up, because there's some sort of faculty initiative for like artificial intelligence research, and I've actually got an idea. So anyway, thanks guys.